Good afternoon, my name is Willem Sonke and I'm going to talk about ordered strip packing. This is joint work with Kevin, Dmitry, Bettina and another Kevin. So our problem is very related to strip packing, in which we are given a set of rectangles with various sizes, as you can see here, and a strip of a given finite width W, and the aim is to place the blocks, the rectangles, in non-overlapping fashion into the strip, and in such a way that the height is minimized. This is a well-known problem, it's NP hard, but in some cases we need a slight variation of the problem. For example, some time back, some of the same co-authors investigated drawing process drawings like this one. And a process drawing needs its steps laid out in order from left to right, and then in several rows. But of course, in this case, if all the rectangles get jumbled up, it's going to be not a very readable diagram. So we need a variation of strip packing here, which we call ordered strip packing. And in ordered strip packing, the rectangles are given in order from 1 to 7 in this drawing, and they are aligned on a spine, the dotted gray line. So each block has a width, and it sticks out by a certain top height above the spine and a certain bottom height below the spine. And the aim is, again, we are given a width W, to break up the blocks in order into rows and place the rectangles on that so that they respect their top and bottom heights. And again, we can minimize the height, or we can also in this setting look at the number of rows and try to minimize that. So we have either a min height drawing or we have a min row drawing. And there's one more aspect that's interesting here, namely we can either allow vertical overlap between rows, as in the drawing on the right. We call it an overlapping row drawing. You can see, for example, that block 4 vertically overlaps blocks on the other rows. And you can also not allow that, in which case you get a left drawing, a non-overlapping row drawing. And this kind of like is a trade-off between saving some height, because overlapping rows vertically saves height, but it might make the drawing a little bit less clear. And you will see in the remainder of this presentation that the results for non-overlapping and overlapping row drawings are very different. So on to the results. I want to talk about two results in this presentation. Firstly, how do we actually compute a minimum height drawing? In our previous paper, with some of the same co-authors, we used a pretty straightforward dynamic programming algorithm to compute non-overlapping row drawings. This takes quadratic time. And we also showed in the same paper that for overlapping row drawings, it's actually NP hard to compute the minimum height. So today I'm going to show you that you can also compute non-overlapping row drawings in linear time. And secondly, we're going to look at these trade-offs between min row and min height drawings. In particular, you can see, not very hard to see, that for non-overlapping row drawings, the minimum height drawing needs at most 2 times the number of rows that the min row drawing needs. So it's kind of like an approximation factor. However, for overlapping row drawings, I think surprisingly, there's not a constant factor that works. It's actually order of log n over log n. So firstly, I will talk about this linear time algorithm for min height drawings, and secondly, I will talk about this approximation factor. So, how do we find a minimum height non-overlapping row drawing in linear time? So for that, let me first talk again about this dynamic programming algorithm, the quadratic algorithm, which works as follows. For each possible row set of blocks, we can basically compute the height, which is just the maximum of the top heights plus the maximum of the bottom heights. And then we just define Ti to be the min height of the first I blocks, and we compute Tn with simple dynamic programming. So we first start by computing T1, then T2, then T3, and then T4, etc., etc. And each of these computations individually takes linear time, so the total algorithm takes quadratic time to run. So how can we do this better? Yes, we can do this better. We can do this in linear time. For now, let's assume that the top height of each block is equal to the bottom height. So that means that the blocks are vertically centered on the spine. Basically what a dynamic program does is compute what the optimal separating block is. So the separating block we define to be the last block on row k-1. And basically if you know the separating block that minimizes the drawing height, then you can recursively compute the rest of the drawing. So the separating block is really all we need to decide. And the crucial insight here is that we need to consider only these separating blocks that wouldn't fit on row k anymore. At least not without increasing the drawing height. Because, for example, in this drawing here, I can take that separating block and it fits on row k. But then I could just as well have taken the previous block as a separating block, because this didn't increase the drawing height. So to be precise, we need to check only these separating blocks that are taller than everything in row k, or that together with everything that was already in row k would exceed the width of the drawing. Okay, so what does that look like? Well, let's assume that we are computing Ti at this moment, and here's a set of blocks. So firstly, we need to consider this block k1, because it's taller than block I. So then we take the next taller block, so we can skip these two white blocks, and then we can go to k2. Then we can skip some more blocks and go to k3 immediately. And then we have a block that exceeds the width, k star. So we basically can ignore all the white blocks here, and we can only look at the blue blocks. And we're going to put these blue blocks into a MinDAG. The MinDAG is a data structure described in 1994 by Kosolobov, and it allows amortized constant times insert, delete, and minima in the DAG. And the way we are doing this is for each block, we are assigning it a value that corresponds to the drawing height if we would take that block as a separating block. So for kj, this is the height of everything up until kj, so that is tkj, plus the height of the next blue block, because that is equal to the height of the last row. So for example here, for k3, we take the height of everything up until k3, and then we take the height of k2 and add it to that, and then you get a total drawing height. And crucially, this is constant. So if we go to the next block I in the next iteration, we don't need to update these values at all. So to update, the only thing we need to do is look at the new block. Assume a new block arrives. We need to update the width, because now, of course, this new block is included in the width. So my block k star might move. I need to remove it from the blue set. And in this case, block I is taller than k1. So k1 is not a candidate anymore. So I need to also remove that. But as you can see, if you do this, because these values stay unchanged in the MinDAG, I only need to insert or delete each block once in my MinDAG. So that means linear number of DAG operations, which is all amortized all one time. So total time is linear. Okay, so that was the algorithm with the assumption that top height is equal to bottom height. If we drop that assumption, it becomes slightly more complicated, but let me give a high-level overview. We do the same thing as before, but we do it separately for top and bottom heights. So we have a top candidate set and a bottom candidate set. It looks like this. We have a blue top candidate set and a red bottom candidate set. And we need to basically consider both sets as candidates. The problem here is that in this case, it's not true anymore that the values are constant in my MinDAG. That is because if I update, for example, if a new block comes in that needs to update the bottom candidate set, it might influence the values in the queue for the top candidate set. So what we do instead is we look at these maximal adjacent sets of blue and red, D1, D2, D3 in this figure, and I put these in each get their own MinDAG, and I put all of these MinDAGs into a larger MinDAG that computes the minimum of the total of all the values. And it turns out that if you do it this way, you can still get the linear time. So please see the paper for more details if you're interested in that. Okay, so that was
how to compute the min-height drawing in linear time. Now a second result, this log n over log n bound. What's happening with that? So we want to know basically how many more rows does a min-height drawing need compared to the min-row drawing. So what we basically want to compute is bounds on something that we call beta n. Beta n is the fraction of the number of rows that the min-height drawing needs compared, divided by the number of rows that the min-row drawing needs. That in the worst case. So as an example to illustrate this, we have two drawings here. On the left we have the min-row drawing. The min-row drawing has 2 rows. And on the right we have the min-height drawing with 3 rows. So this example shows that beta n is at least 1.5. And so the question is beta n constant? Well, for the longest time actually we thought yes while researching this. So we tried to prove 2, didn't work. We tried to prove 3, didn't work. We tried to prove 4, didn't work. And then at some point one of the co-authors of this paper, which is not me, came into the room and said, well, I think I found a lower bound for log n over log n. So no, and let's see this lower bound. So this is a picture that maybe it's slightly complicated. Let me walk you through it. If you look at the top picture, this basically shows the min-height drawing for the lower bound. And this is not to scale, and the numbers on the left side of the drawing indicate the actual heights. And you can see there's an exponential decay here. And that is on purpose because that makes it so that if I take any block from a row and put it somewhere else, I'm going to increase the drawing height. And that makes it so that this is the only possible min-height drawing that you can get. And indeed, it has 5 rows. So I do this thing for k is 4, so that is k plus 1 rows. I can also draw it for, you can do this for whatever k you want. And on the bottom side, on the bottom of the screen, you see the min-row drawing for this, and you see everything fits nicely onto 2 rows. So we have an example with k plus 1 rows in the min-height drawing and 2 rows in the min-row drawing. And if you compute this, you get log n over log n for beta n. Okay, so let's try to do the matching upper bound. So we want to show that if we have a min-row drawing with r rows, then the min-height drawing always has at most r times c log n over log n rows. And the way we're going to do that is let's assume we are given a drawing, a min-height drawing with too many rows. Well, then let's show that we can merge 2 subsequent rows together without increasing the height. And I can warn you beforehand, this is going to be a very high level overview only. Again, the complete details are given in the paper. So given this drawing, we want to merge 2 rows. And the first thing we're going to do is find a large enough set of adjacent sparse rows. And sparse rows are simply rows that do not have too much of their width occupied by blocks. And this always exists, this set of sparse rows, because we have too many rows. Okay, and then in this set of sparse rows, I'm going to take all the blocks and move them to the left as much as possible. So if this is my set of sparse rows, what I'm going to do is I'm going to take my first row, keep it fixed, but then I'm going to sweep all of the remaining blocks, I'm going to sweep them to the left as much as possible until they hit something else. Okay, so now we get this thing where everything is basically swept to the left. And what I want to show now is that the last row has all blocks clustered. So why is that helpful? Well, if all the blocks are clustered, then we can basically repeat this construction from the other side. Then we have 2 rows with 2 adjacent rows having the blocks all clustered, and that gives a very nice structure. Then you can show somewhat easily that you can merge these rows together. So how are we going to show that the last row in this construction has their blocks clustered? Well, what you would want to argue is that the number of clusters just monotonically decreases per row. But it's actually not true, because you don't know anything about the blocks that are on each of these rows. So that's very complicated and not even true. So that doesn't work. But what does work is we can observe that from top to bottom, these spaces between, the free space between the blocks becomes more and more orderly somehow. So we take a measure of order from information theory that's called entropy.
And then we show that between two rows of this construction, the entropy always decreases by at least some constant number. Again, math is completely worked out in the paper, of course. And then you can show that on the last row, because we have this constant decrease, there's basically no entropy left, or like only a small amount of entropy is left on the last row. And that implies that all blocks are clustered. And that proves the upper bound. Okay, so to conclude, for min-height drawings, I showed a constant time algorithm to compute non-overlapping drawings. And we also studied these trade-offs, and we have this, in my view, surprising log n over log n bound for the number of rows a min-height drawing needs. Thank you.
Yeah. Let me ask you. So this is obviously intended for technical drawings. Is it also useful for VLSI layout?
Can you hear me? Okay. We haven't thought about VLSI layout in particular. I could imagine it could be useful if you want to lay out components in order, but I know very little about VLSI layout, so I cannot really answer that. One other application we had in mind is, for example, typesetting of text. Like a little bit like LaTeX does it, for example. Like it's a paragraph of words, and obviously you want your words to be in order.
Mm-hmm.
So imagining you would have a paragraph where some words, or like formulas, have like need more height than other lines. Then maybe the overlapping rows drawing could be used to like make the text fit in a smaller amount of vertical space.
Okay. Any other question? Yeah, there is the question.
I would like to know the future direction you have in mind for this work. For example, the linear time algorithm is it's amortized linear, if I understood it. Is it?
So the DEX we use are amortized constant, but that amortizes up to a linear, like a worst case linear algorithm. Maybe to answer your first question, future research directions, to be completely honest, we don't exactly know. So this originally came from this paper, like we had this paper 2 years ago, that was at the visualization conference that was about these technical drawings, and like that was the application area we originally got it from. I could imagine that you can use it for other things as well, and if like anyone has of course ideas on how to use it, then I would love to know that.
Mm-hmm. Thank you.
Okay. Yeah, actually time is also basically up, so in about 1 minute we will continue. Thank you.